One of the deepest unsolved questions in math is about how primes behave. Every time you bank online or send a private message, you're relying on the properties of prime numbers. But we still don't fully understand them. In fact, a single sentence written down in 1859 has stumped everyone who's tried to prove it. Welcome to Voyager, where we investigate the biggest unsolved mysteries in math, science, and engineering. Today, we're exploring the Riemann hypothesis.
The Riemann hypothesis is the oldest of the $7 million problems, and is probably the most famous problem in mathematics now that Fermat's last theorem has been settled.
On August 8, 1900, David Hilbert stepped onto a stage and gave what many consider to be the most consequential lecture in the history of math. To an audience at the International Congress of Mathematicians, he laid out 23 problems he believed would define the century to come. Eighth on his list was a conjecture proposed 40 years earlier by Bernhard Riemann about where the zeros of a particular function lie. While this may sound simple to state, the conjecture turned out to be almost impossible to prove.
Riemann hypothesis, I have no clue. I mean, it has to happen by accident. Usual techniques cannot hope to settle this question. The proof has to come out of left field. But what that is, no one has any serious proposal.
It haunted Hilbert for the rest of his life, and he reportedly told a colleague that if he were ever woken up after sleeping for 500 years, his first question would be, had anyone proven the Riemann hypothesis? 100 years later, the Clay Mathematics Institute announced a $1 million prize for anyone who could solve it. Today, it's often considered one of the greatest unsolved mysteries in math. What makes this hypothesis strange is not the difficulty. Math is full of hard problems, with many still left unsolved. What makes the Riemann hypothesis strange is that the field has, in the words of Fields Medalist James Maynard, no plausible line of attack. It isn't that mathematicians have tried everything and failed. It's that after 160 years, they still don't even know where to start. And despite hundreds of other theorems resting on the assumption that it's true, and a $1 million prize waiting for whoever settles it, almost no one is even trying. Over the years, people have claimed to crack it, researchers have checked it in trillions of cases, there's even a mysterious connection to quantum physics that no one can explain. Yet after more than 160 years, the proof is still nowhere to be found. So why can't anyone solve the Riemann hypothesis? We're going to investigate this case, laying out the evidence, building the timeline, and weighing the competing theories and approaches. But before getting into the theories, let's go back to the beginning. Where did the hypothesis come from, and what does it actually say? In November 1859, the Berlin Academy received a short paper from a 33-year-old mathematician. It was only 8 pages long, and modestly titled, On the Number of Primes Less Than a Given Magnitude. Its author, Bernhard Riemann, had been elected to the Academy that summer and was expected to submit something to mark the occasion. This was it, and he never published on number theory again. Riemann was painfully shy and chronically ill. He'd grown up the son of a Lutheran pastor in a village in the Kingdom of Hanover, the second of 6 children, and his early letters home dwell on poverty and homesickness more than math. And a few years later, while traveling, he died of tuberculosis at age only 39. And here's where the trail almost goes cold. After his death, his housekeeper burned a stack of his unpublished papers before his colleagues could stop her. Whatever Riemann had worked out in his notes, some of it went into the fire with those pages. Inside the 8 pages he submitted to the Academy was an interesting parenthetical remark. Riemann was studying a function, now called the Riemann zeta function, whose behavior, he realized, seemed to govern the distribution of prime numbers. While ancient Greeks, like Euclid, proved that there are infinitely many primes, Gauss in the 1700s first discovered that the frequency of primes isn't entirely random. By hand counting primes in tables, Gauss noticed that as the numbers get higher, the probability of finding prime numbers diminishes in a predictable, logarithmic pattern. This discovery laid the foundation for modern analytical number theory, and Riemann took it one step further. Gauss's pattern was only an average. The real primes don't follow it smoothly, they're scattered around it in a way that looks like noise. Riemann found where that noise comes from. Buried in the zeta function is a special set of points. It's zeros, and each one contributes a correction to Gauss's estimate. Add up the corrections from every zero, smooth the average, and the smooth average sharpens into the exact count of the primes. The zeros of Riemann's zeta function are what turn the approximate pattern of the primes into a precise one. And the position of each zero decides how much it matters. One coordinate of the zero controls the size of its correction, how far it can push the primes away from Gauss's average. And Riemann noticed that every complex zero he checked had a real coordinate set to the exact same value, 1/2. The Riemann zeta function not only suggests that the primes are not random, but that the zeros of the function encode the primes distribution. This came from Riemann's observation that all the non-trivial zeros he had examined sat on a single vertical line. And in a footnote in his paper, he wrote that it was very probable that they all did. That is the Riemann hypothesis. And it rests on an idea that has intrigued mathematicians ever since. The primes look random. No pattern has ever been found, yet the zeros of one function appear to obey a hidden rigid order, and Riemann's claim is the strongest form of that order possible, that every single zero sits exactly on the same line. The entire case comes down to whether that line holds. So let's look at it closer. Why is it 1/2? The zeta function satisfies a functional equation relating values at s and 1 minus s, which makes the axis of symmetry of the real part exactly 1/2. The function is built with a perfect symmetry centered on that line at 1/2. That symmetry then forces the zeros to be arranged in a balance around the line. For every zero on one side, there has to be a mirror image on the other. So the zeros are always going to cluster around that line. Riemann's conjecture is just a stronger claim, that they don't just cluster near it, they all sit exactly on it, with nothing straying to either side. Now let's get into the theories and approaches. 3 separate leads have pointed to the same verdict, that Riemann was right, but not a single one of them is able to prove it. And the first lead is the strangest. And it began by accident, over a cup of tea. Before I get into that, if you're enjoying this video, please like and consider subscribing. I really appreciate your support. Let's get into it. In the spring of 1972, a graduate student named Hugh Montgomery was visiting the Institute for Advanced Study in Princeton. He had been working on a formula describing how the zeros of the Riemann zeta function were spaced along the critical line. Maybe the spacing of the primes would provide some insight into the function. At tea one afternoon, he was introduced to Freeman Dyson, a physicist. Dyson asked what Montgomery was working on, and Montgomery showed him the formula. Dyson recognized it immediately, because it was the same formula physicists use to describe the spacing of energy levels in heavy atomic nuclei. Systems like uranium, with hundreds of protons and neutrons, interacting in ways too complicated to solve exactly. And this is known as quantum chaos. The gaps between the Riemann zeros and the gaps between the nuclear energy levels follow the same distribution. A numerical comparison across billions of zeros has confirmed the match to extraordinary precision. But why would abstract prime numbers have a connection to subatomic particles? In quantum mechanics, the measurable properties of a system, the energy levels of an atom for example, are extracted using a mathematical object called an operator. An operator is a rule that acts on functions similar to how a derivative acts on a function to produce another one. When you apply the right operator to a quantum system, the numbers that you get out are called eigenvalues, and those eigenvalues are the values you would actually measure in a lab. For example, the energy levels of hydrogen are the eigenvalues of an operator called the Hamiltonian. Now there's a special class of operators called self-adjoint operators. These come with the guarantee that their eigenvalues are always real numbers, never complex. Physics relies on this because measured energies in the real world are real numbers, and this is the link to Riemann. A non-trivial zero of the zeta function is a complex number. The Riemann hypothesis claims that every such zero has the form s equals 1/2 plus it, where t is a real number. The 1/2 is the critical line. This is the real part of the complex number. The t in the imaginary part is what changes from 0 to 0. So each zero is fully described by its t value, and that t is a real number. So then the question is there a self-adjoint operator that gives these eigenvalues that are the same as the t values of the zeta function zeros? Finding a self-adjoint operator would prove the Riemann hypothesis true if and only if you could establish 2 things about it. Its eigenvalues have to be exactly the t values of the Riemann zeros, and it has to be proven to be self-adjoint, because only self-adjointness forces the eigenvalues to be real, and only real t values put every zero on the critical line. Decades before the tea at Princeton, David Hilbert, who we saw initially named the hypothesis as one of the most important math questions, and Hilbert-Pólya had independently suggested that the t values, not the zeros themselves, but the real numbers that describe the location in the complex plane, might be the eigenvalues of some unknown self-adjoint operator. If true, the Riemann hypothesis would follow automatically. The eigenvalues would be forced to be real by the operator structure, which means every t value would be real, which means every zero would sit on the critical line. This theoretical concept is called the Hilbert-Pólya Conjecture, and the math community has been searching for this operator for over a century. Many candidate operators have been suggested. Some have eigenvalues that resemble the t-values statistically. Some come from elegant physical or geometric constructions. but none has been proven to satisfy both conditions simultaneously. More than 100 years of searching, and the object that would resolve the hypothesis has yet to be found. The Montgomery-Dyson tea-time coincidence in 1972 was so exciting because it was the first concrete evidence that such an operator might really exist, and not just as a piece of math. The quantum evidence raised a stranger possibility, that the operator is a real physical system, a particle or an arrangement of energy levels that we might be able to measure in nature, but no one ever has yet. So the Hilbert-Pólya physics approach ends where it starts, with an object everyone is convinced is out there, but no one can produce. The second lead we're going to look at comes from a completely different direction, geometry. Down this road, the Riemann hypothesis has already been proven, just not for our number system, and it begins in a prison cell. In 1940, the French mathematician André Weil was sitting in a military prison. He had been arrested for failing to report for duty at the outbreak of the war, and he would spend several months in the cell before being transferred. During that confinement, he did some of the most important work of his career. Among other things, he sketched a proof of a statement that looked almost identical to the Riemann hypothesis, except it was about a different kind of mathematical object entirely. Weil's theorem is sometimes called the Riemann hypothesis for curves over finite fields. It's a real theorem with a real proof that has been accepted. The strange thing about it is what it implies, that the Riemann hypothesis is true, just not in our world, in a parallel one. This parallel world is the world of finite fields. In ordinary math, the integers stretch off to infinity in both directions. A finite field is a number system with only a finite quantity of elements, sometimes only a handful, but in which addition, subtraction, multiplication, and division still all work in the expected ways. Mathematicians can build geometric objects, called varieties, out of these finite systems, and they can attach zeta functions to these varieties that look very similar to the Riemann zeta function. And Weil proved that the zeros of those zeta functions all sit on a critical line, exactly what Riemann had conjectured for the integers, except here it's accepted proof. But this lead didn't stop with Weil. In 1974, Pierre Deligne extended Weil's result to higher dimensional varieties, completing what had been a 50-year program and later winning the Fields Medal for the work. And the result only grew more general. Selberg later proposed an axiomatic framework called the Selberg class, suggesting that the Riemann hypothesis is one instance of a deeper structural law that applies to a wide variety of zeta-like functions. So the proof exists. The problem is that it cannot be carried over to the domain of infinite integers. The proofs that work in the parallel world depend on a way of doing geometry on objects built from finite fields that has no current equivalent for ordinary integers. Integers do not sit on a surface that can be analyzed with the same tools. To use Weil's proof for the Riemann hypothesis, mathematicians would need to invent a geometry of the integers themselves. And decades of effort have not produced one. So the geometry approach, like the physics approach, seems to point to an elegant answer that we can't describe yet. But the third approach gives up on this elegance entirely. If you can't prove the hypothesis, you can at least go hunting for the one thing that would disprove it, a single zero in the wrong place. So mathematicians started counting the zeros and checking to see if they all fall on the critical line. And in 1955, the counting almost ended the whole story. In 1955, D.H. Lemmer fed punch cards into a refrigerator-sized computer and waited. He was calculating the first 25,000 zeros of the Riemann zeta function, more than anyone had ever attempted. And somewhere around the 6,709th zero, the printout did something nobody had seen before. 2 zeros almost touching, a gap of only 0.04 in a region where the average gap is 1. For half a second, it looked like the Riemann hypothesis was about to be disproved. It wasn't, but this was the first incident where it seemed like it might be possible. And this has kept happening at different zero locations. If the hypothesis is ever going to be disproved, mathematicians believe it will fail when 2 zeros almost touch. Here's why. We know the non-trivial zeros of the zeta function are expected to live in the narrow band called the critical region, but there's also a second claim that every zero is simple. Each one is a distinct point. When 2 zeros sit unusually close, 2 things could happen that would disprove the hypothesis. Either the 2 zeros merge into a single point on the critical line, meaning they're actually 1 zero, or the 2 points are not on the critical line at all. In a simulation, 2 points might appear to be on a line, but a computer can only measure down to a certain precision. In reality, those points might be a mirrored pair sitting just off the line. Or they might even be the same point. but the Hilbert-Pólya conjecture only works if every zero is unique. So how close is the hypothesis to being disproven? Well, there's actually a number that measures this. De Bruijn and Newman proved that there's an exact constant, they called it lambda, below which all the zeros stay real and above which the zeros become complex. So essentially, the Riemann hypothesis is equivalent to the statement that lambda must be less than or equal to 0. For decades, that left a lot of room to spare. Lambda could have been any number less than 0, and still the hypothesis would hold. But in 2018, Terence Tao and Brad Rogers proved that lambda must be greater than or equal to 0, meaning that there's only one possibility that makes the Riemann hypothesis true. Lambda must be exactly 0. As lambda is a parameter that measures how close the Riemann zeros are to being purely real, it quantifies that the Riemann hypothesis is only barely true. Proving that lambda is anything else than 0 would now completely solve the Riemann hypothesis. And Tao has continued to work on this, initiating a collaborative polymath project to push down the upper bounds on the constant. At this point, it seems like all theories and no progress. Almost as if we're no closer to actually solving the hypothesis than Riemann himself was in 1859. But there actually has been measurable progress towards solving the mystery. And many have even claimed to solve it. In 1914, G.H. Hardy stands on a dock and before departing on a trip, mails a postcard with the message, "I have proven the Riemann hypothesis." He hasn't yet, but the sea is rough and he has worked out his insurance. If the boat goes down, the world will think he has died holding the proof, and God, Hardy reasoned, would never hand him that kind of glory, undeserved. So the boat would not be allowed to sink. Hardy survived the journey, and later did end up proving something. Not the whole hypothesis, but the fact that infinitely many zeros lie on the line. Infinitely many sounds like a lot, but in an infinite total, it can still mean 0%. He had proven an infinite amount, and in proportion, nothing at all. However, it was enough for the next generation to pick up the case. In 1942, Selberg pushed the proven fraction above 0. This was the first time anyone had shown that a positive share of all the zeros lay on the line. 3 decades later, mathematicians forced it to 33%. By 1989, it was 40%, and in 2011, 3 mathematicians increased the percentage by a single point to 41%. In 2024, James Maynard and Larry Guth carved out broad near regions where stray zeros simply cannot be located. The first real progress in decades. But Maynard, like Tao and many others who've studied the problem, has said that finishing the work will take some big idea from somewhere else. So, if the idea has to come from somewhere else, does it have to come from a person at all? In 2025, Google DeepMind aimed neural networks at the Navier-Stokes Millennium problems and uncovered entire families of unstable fluid singularities that had stayed hidden from mathematicians for a century. In 2026, their alpha-proof Nexus system solved 9 open problems, 2 of them open for 56 years. AI seems to be resolving open problems more and more. But these methods applied to the Riemann hypothesis so far are only able to check zeros. And so far, 12 trillion zeros have been checked. But while everyone is on the critical line, this is still not enough for a proof. And here's why no amount of checking will ever be enough, no matter how high the computers count. In 1933, Stanley Skews showed that patterns in the primes can hold for astronomical stretches before flipping, meaning that even these trillions of examples guarantee nothing. A pattern that holds for 12 trillion cases can still break at the 12 trillion and first. The computers, like the mathematicians, can observe a pattern but can't explain it yet. So what would a big idea from somewhere else even look like? In 1959, John Nash stood before an audience at Columbia University to present his solution. The room had come expecting a breakthrough from one of the sharpest minds alive. Instead, the lecture was incoherent, one of the first public signs of the illness that would hospitalize him. Nash was one of the most original mathematicians of his century, and he had taken on the Riemann hypothesis as the ultimate test. This problem doesn't draw the unqualified, but draws the most capable people alive. De Bruijn, who settled another famous conjecture, has actually released manuscript after manuscript claiming to approve the Riemann hypothesis since 2004. Specialists have shown that the approach, as he frames it, however, cannot work. De Bruijn closed the Bierbach conjecture, a problem that had stood for nearly 70 years, proof that problems once called impossible can eventually be solved. But after decades of manuscripts and claims, the field has not accepted his, or anyone else's, proof of this one. Then there's one last possibility. What if the reason no one can find the proof is that there is no proof to find? Some researchers suspect that the Riemann hypothesis may be undecidable, that under Gödel's incompleteness theorems, it's a statement that can neither be proven nor disproven. And underneath it all, the question we started with is still open. Every approach has been a different way of asking one plain thing about prime numbers. Are they as orderly as they appear? Or does that order diverge somewhere we haven't looked yet? So we are left at a peculiar standoff. Computers have checked trillions of zeros, the spacing between those zeros match the spacing of energy levels in quantum systems, a version of the hypothesis has actually been proven over finite fields, and at least 41% of all zeros have been shown to lie on the line. But that's not all. For decades, mathematicians have written theorems that begin with the words, if the Riemann hypothesis is true. When someone later manages to prove one of those conjectures without assuming the Riemann hypothesis, the conclusion still turns out to be correct. So if proofs that depend on it are true, where is the proof of the Riemann hypothesis itself? Which approach, if any, do you think will reach a proof first? Make your case in the comments. And if this is the kind of content you want to keep seeing, subscribe. I try to investigate questions in science and math every week, and if you like the story about the Riemann hypothesis, you might also like my video on another one of the Unsolved Millennium Prize problems. It's on screen now. I'll see you in the next one.